Hello and welcome to the AICE Chemistry Lecture Series. Today we're going to look over Chapter 6, Section 5, which is going to cover bond energies and enthalpy changes associated with both bond formation and bond breaking. So let's get right into it. Bond breaking and bond formation are essentially the two aspects that always are going to happen during chemical reactions. When we have a chemical reaction, the reactant bonds need to be broken, whereas the bonds for the products need to be formed. So in this process, we're always going to have at least one of the two during a chemical reaction, either bond formation or bond breaking. At the core of all the enthalpy change calculations that we have done throughout this chapter, bond breaking and bond making, as well as intermolecular forces being formed or breaking, are going to be at the core of what dictates the enthalpy changes. And this is very straightforward. Bond breaking, so the breaking of bonds or attraction, so intermolecular forces would also fall into this category. So the bond breaking or intermolecular force breaking is always going to require energy. And therefore, it's by nature an endothermic process. The breaking of bonds, so if we have, for example, hydrogen molecules here, it takes energy to break the bonds that hold atoms together. Same thing with intermolecular forces. If we have intermolecular forces, it takes energy to break those intermolecular forces. Meaning the process of bond breaking and intermolecular force breaking is always endothermic. On the other hand, on the other side of that spectrum, bond or intermolecular force formation, the creation of bonds or intermolecular forces, being the opposite process, is always going to release energy. And is therefore always an exothermic process. When atoms come together and bonds are formed between those atoms, that process of the bonds forming releases the energy that is potential energy stuck in those bonds. And so bond formation or bond making is always going to be exothermic. It's always going to release energy. So it's very important for you to know, because at the very core of chemistry, at the very core of thermodynamics, this is what it's all about. Any process that breaks bonds or breaks intermolecular forces is going to be endothermic. Whereas any process that forms bonds or intermolecular forces is always going to be exothermic. And therefore, a process that does both, it creates bonds and breaks bonds, is going to depend on which of the two processes is more endothermic or exothermic. So which one releases or uses more energy. So whether a reaction is endothermic or exothermic is directly going to depend on whether the process of breaking bonds or intermolecular forces in the reaction is higher or lower in energy than the release energy from the formation of the product bonds. Because reactants are always going to have their bonds broken, whereas products are always going to have their bonds formed. Because we break apart reactants and we form products. So let's look at this in a visual manner. We can do energy level diagrams in order to visualize endothermic and exothermic reactions by creating both arrows up and down to show bond formation and bond breaking. For example, this is the energy diagram, and it's a bit different than the energy level diagrams that we've seen before. This diagram uses up and down arrows to show either an endothermic process or an exothermic process, respectively. So an endothermic process will have the arrow pointing up. Oops, let me make that a little better. So an arrow pointing up denotes an endothermic process, whereas an arrow pointing down shows an exothermic process. And this is because the y-axis on this type of energy level diagram or energy diagram is energy. And so anything that is endothermic is going to take something from a different color. It's going to take something from one energy state, and once it absorbs that energy, it takes it up to a higher energy state. So that's why vertical arrows pointing up are going to denote endothermic processes. On the other hand, for an exothermic process, we're going to have an arrow that points down. Why? Because if something's at a certain energy and then it releases energy, it means that it's going to come down to a lower energy state. That's why that energy is being released. So this energy level diagram uses the y-axis to show energy, just like the energy level diagrams that we saw earlier did. But in this case, we have a much more square-looking diagram. It's not like the other one that showed the process of the reaction with activation, energy, and everything. This type of energy diagram is just to show the different levels of the different processes, the reactants, the products, intermediates, etc., etc. So if we look at this energy level diagram here, we can see that, for example, in the reaction that burns methane. So this energy level diagram is for, let me write it up here. It's for the following reaction: CH4 reacting with O2, two O2s, to yield CO2 and two H2Os. So what we're looking at here is this reaction. We have our reactants in the left side of the diagram. So here we have our methane and our two oxygens, which are our reactants here. And then we have our products, carbon dioxide and water, here at the bottom. This is because our methane burning in oxygen is an exothermic process. Our delta H here, which is symbolized by this arrow, because we're going from the reactants to the products, is negative delta H. And we can see that because this arrow is pointing down, meaning that when methane reacts with oxygen, when it burns, it releases energy, creating carbon dioxide and water. And that's why we have the negative arrow. Well, that is one, we call it a path, just like we did earlier with the other chapter or their section. That path of energy being released, right here, is the direct reaction that we have in the reaction. It's the reactants becoming the products. But we can think of this as two separate steps. Just like we did with Hess's law and energy level diagrams, we can think of this process not happening directly, not just methane reacting with oxygen to create carbon dioxide and water. We can instead think of it as an alternate path. And what would that alternate path look like? Well, that alternate path happens in two steps. Step number one is all of the bonds in methane and and oxygen breaking apart. That will mean going into here, grabbing all of these CH bonds in methane and breaking them. Let's do this. So we will be breaking all of these CH bonds in CH4, and then grabbing the two oxygen-oxygen double bonds in methane and breaking those. If we do that, what we end up with is just individual atoms. So we can break every single bond in these two molecules, in these three molecules, in these reactants, and end up with one carbon atom, 4 hydrogen atoms, and 4 oxygen atoms. That process, because the only thing we're doing in that process is breaking bonds, that delta H for that process is always going to be positive. It's always going to point up. Because remember what we just talked about, bond breaking is always endothermic. Well, once we have those atoms individually, like we have here, what we can then do is we can grab all those individual atoms and we can create our products from them. So essentially what we did here was deconstructing the reactants by breaking all their bonds into individual atoms. And then by doing that, we can grab the individual atoms and we can create the carbon dioxide molecule and the 2 water molecules by joining a carbon and 2 oxygens with double bonds, and by joining oxygen with 2 hydrogens in 2 different molecules with single bonds. And that process of bond formation is going to be exothermic because bond formation is always exothermic. So this delta H right here is positive. Sorry, it's negative. That delta H right there is negative because bond formation is always exothermic. Meaning we can see a reaction, and this could be any reaction. In this particular case, we have a combustion reaction. But we can see this reaction as happening in two separate steps, looking at bond breaking all the bonds in the reactants to get atoms, and then bond formation, which means that we will grab all those atoms and create the bonds that are resulting in the products. The first step being always endothermic, the second step being always exothermic. So if we visualize our reactions in this manner, what we end up with is essentially that whether the reaction's endothermic or exothermic is going to depend mainly on or solely on whether the energy needed to break all the bonds is higher or lower than the energy needed to or released by forming all the bonds. So if we look at it here, this is an exothermic reaction. How do we know that? Well, the vertical bond breaking endothermic process is smaller, literally smaller, than the exothermic bond formation. So because of this, the energy needed to break the bonds being smaller than the energy released by the bond formation, in total, we have an exothermic reaction because more energy is released than the energy that is absorbed. And so in total, the reaction releases energy. On the other hand, if we had an endothermic process, like this one, we will have the opposite process, or the opposite case. In this particular case, if we have our reactants, I'm going to highlight them in the same color so we can follow along more easily. In this endothermic process, if we look at our reactants in this reaction, and in this reaction we have hydrogen bromide, 2HBr. I'm going to draw the reaction up here. So we have 2HBr being decomposed back into hydrogen and bromine. So again, to use the same color coding, if we highlight our reactants yellow, then the reactants are right here. We have those 2HBr molecules. If we highlight our products blue, then our products are right here. We have the H2 and the Br2 molecules. So here, again, where is our reaction? Where is our reactants becoming the products? Well, our reaction is right here. We have the reactants, HBr, becoming the products H2 and Br2. And we can see that reaction right there, that process, the delta H, is going to be positive because that arrow is pointing up. Why is this one positive whereas the other one was exothermic, was negative? Well, if we look at the individual steps, if we look at the bond breaking here, the bond breaking the HBr bond is positive because always bond breaking is always going to be positive. So we have delta H here is going to be positive for the bond breaking. But then the bond formation, like always, is going to be negative. Or it's going to be exothermic. So delta H for bond formation here is going to be negative. So what's the difference between the two reactions? Well, look at the size of the arrows. In this case, the bond breaking, the endothermic process, is much more energetic, requires a lot more energy than the bond formation releases. Because the bond breaking requires more energy than the bond formation releases, or another way to put that is because the endothermic process absorbs more energy than the exothermic process gives off, in total, the reaction absorbs energy. because there's not enough energy released by the bond formation to make up for all of the energy used during bond breaking. And so our enthalpy change is, in total, is positive. So that's the main difference when it comes to bond formation and bond breaking of an exothermic versus an endothermic reaction. In an exothermic reaction and an endothermic reaction, bond breaking is always endothermic, bond forming is always exothermic. So the difference between the two is simply which was bigger. In an exothermic reaction, bond breaking absorbs less energy than the bond formation releases. In an endothermic reaction, the one on the right, bond breaking absorbs more energy than the bond forming releases for the products. So that's just a way of thinking about endothermic and exothermic processes in the AICE or in the scope of bond formation and bond breaking. But it will make it a lot easier if we actually had a way to talk about this, right? And we do. It's called bond energy. Bond energy is the measure of the amount of energy of individual bonds with their exact bond energies. So it's the energy needed specifically not to form but to break a specific covalent bond in a named molecule in the gaseous state. So what is essentially bond energy? If we grab a specific bond, like a carbon-hydrogen bond in methane or a carbon-hydrogen bond in ethane, and we wanted to break it, the amount of energy needed to break that bond would be what we call the exact bond energy. Now, because this is bond breaking, bond energies are always endothermic, they're always positive. If we wanted to figure out how much energy is needed, is released when the bond is formed, all we will have to do is do the exact bond energy, but with a negative sign in the front, because it will require the same energy, or it will release the same energy as it will be required to be broken. Now, while the bond energies, or the exact bond energies, are something that is, somewhat used sometimes in very specific chemistry, it is not good for general chemistry. It's not good for a generalized chemistry approach. Why? Because when we talk about the bond energy of the CH bond, it is going to depend on the environment of the bond. Meaning the CH bond in methane, in CH4, does not have the same exact bond energy as the CH bond in ethane, in C2H6. You can see here the exact bond energies for the CH bond in methane is slightly different than the one for ethane. The one in methane has a bond energy, exact bond energy of 415.48 kilojoules per mole, meaning it takes 415.48 kilojoules to break 1 mole of CH bonds in methane, whereas in ethane it's 413.00 kilojoules per mole. So it is not a lot different, but slightly different. So for general calculations, that doesn't make a lot of sense, because imagine how many molecules have a CH bond in them and how many small little differences we have. For general calculations, we use what is called the average bond energy, not the exact bond energy, which is an approximation. So we use the average bond energy when we want a very good approximation. Always it's not going to be perfect, but it makes it so that we don't have to look at the specific molecules all the time. The average bond energy is simply the energy needed to break a specific covalent bond averaged from a variety of molecules in the gaseous state. Always in the gaseous state. So that's very important. When we're breaking bonds, we're doing so in the gas state. That's the definition of bond energy. So it's the amount of energy needed to break a specific bond in the gas state of the molecule, but this is an average, meaning that we are going to grab all the exact bond energies of the CH bond in methane, the CH bond in ethane, and the CH bond in every molecule that has CH bonds in it, and that average is what we call the average bond energy. So when we actually do mathematics in the next section, this is what we're going to use. We're going to use the average bond energy, not the exact bond energy. We're never going to need to use the exact bond energy in this class. You just need to know that the exact bond energy is the bond energy for that specific bond in a specific molecule, whereas the average bond energy, which is what we actually use, is the amount of energy needed to break that bond in the gas state, average from a variety of molecules, from everything, essentially all the molecules that have that particular type of bond. So that's the theory behind bond energy and the energetics behind bond energy. In the next section, we are going to look at how do we use these numbers, these bond energies, in mathematics, and how to use them with Hess's law. It is actually fairly straightforward because it's going to look a lot like the conversation we had earlier in another video about Hess cycles with chemical reactions. That's it for this video. I will see you all in section 6.